Good afternoon, everyone. I am Burçin. I'm the Executive Director at the Institute for Policy Integrity at New York University School of Law. Policy Integrity is a nonpartisan academic think tank dedicated to improving the quality of governmental decision-making. We use economics and law to support smart policies for the environment, public health, and consumers. And we're delighted to welcome you to today's webinars. Today's conversation is the first in a series of webinars organized by Policy Integrity with the generous support of the Alfred P. Sloan Foundation. Our goal in these conversations is to highlight cutting-edge interdisciplinary research on energy and environment, and to bridge the gap between this amazing research and real-life policymaking. So with that goal in mind, we have academic researchers supported by the Sloan Foundation, as well as policy experts working on energy and environment issues day in and out. So we hope that these conversations inform policymakers with the latest insights from research and result in better policies. And at the same time, we hope that these conversations help researchers to think about more policy relevant questions and how to focus their research for a better policy impact. Today's conversation is on a very critical decarbonization issue, industrial decarbonization. We will focus on efforts to decarbonize various industrial processes that are hard to decarbonize, including chemicals and steel and chemicals manufacturing. Well, we will discuss the technological and policy changes needed to achieve these shifts, as well as the role of academic research in these policymaking processes. Today's conversation is going to be moderated by Derek Sylvan. Derek is a strategy director at Policy Integrity, and his work focuses on sustainable infrastructure and decarbonization strategies. Derek, microphone is yours.
Great, thank you, Burçin. So as mentioned, I'm Derek Sylvan. I'm the strategy director at the Institute for Policy Integrity. I want to thank you all for joining us today to discuss a really critical topic, industrial decarbonization. As you're all likely aware, there's a very short timeline for deep decarbonization to occur if society is going to limit the worst impact of climate change. And some of the activities that are central to the global economy are among the hardest to decarbonize. In particular, heavy industry presents a huge challenge. So major changes are needed in the way we produce steel, chemicals, cement, and a host of other materials that are essential to society. And in navigating that process, there are a lot of technical questions to figure out, as well as questions of practicality, implementation, market, cost, job impacts, and many others. And given the tight timeline for this transition, there is very little room for trial and error. So we need to learn as much as possible about this process as quickly as we can. Luckily, there are some incredibly talented researchers around the world working to help answer these questions, and we'll get to hear from a few of them today. So it's especially important that research projects in this space are designed to yield findings that are actionable and not just academically interesting. And it's also important that the approaches to industrial decarbonization that seem promising are tested in real-world settings so that implementation questions can be figured out. And that will then pave the way for the policies and investments that can help clean up industrial activities. In particular, the U.S. Department of Energy is doing some pioneering work in that area, so we'll hear some more about that today. And we'll also have a chance to hear from researchers who are helping clarify some of the most promising ways to decarbonize industrial processes and exploring the related impacts. So I'm excited to hear from all our panelists today. Each of our speakers will give a short presentation, and then we'll have time for discussion and questions. You can submit questions through the Zoom Q&A function at any time while presenters are speaking, and then we'll get to as many of those questions as possible once all the presentations are finished. So to start things off, I'd like to introduce Dr. Erin Mayfield. She is an assistant professor at Dartmouth College in the Thayer School of Engineering. Her research is in the areas of sustainable systems engineering and public policy, with a focus on energy and environmental system transitions in the context of climate change. She previously held positions at Princeton University, the U.S. Environmental Protection Agency, U.S. Congress, and the Environmental Law Institute. So I will hand things over to Dr. Mayfield to discuss some of her current research.
Great, thank you. Good afternoon. I'm Erin Mayfield. I'm an assistant professor at Dartmouth College. My presentation today is about ongoing research on integrating cost, climate, and equity objectives into steel infrastructure planning and decision-making. This research project, which is funded by the Sloan Foundation, is ongoing. So this is the first year of the project. So in this presentation, I'm focusing on the design of the research project and methods rather than results. By way of background, the steel industry is a major source of greenhouse gas emissions, accounting for about 7% of global carbon dioxide emissions. The US steel industry is the fourth largest producer in the world, and it's comprised of on the order or over 100 operating sites that are geographically concentrated in the Midwest and are also disproportionately located in disadvantaged communities. There's a range of different mitigation options for the steel industry, including things like direct electrification of industrial processes, replacement or expansion of current electricity supplies with low carbon sources, switching fossil fuels to lower carbon fuels and feedstocks like hydrogen and biomass, and adoption of CCS. However, there's no single solution for decarbonizing the steel industry, and many factors have the potential to influence industry and plant level decarbonization strategies, such as technology costs and their efficacy, future kind of demand for materials and products, trade and industrial policies, in addition to distributional and procedural inequities that are embedded in our legacy infrastructure. Insights from computational decision support tools are increasingly being used by policymakers and planners for agenda setting, funding allocation, and infrastructure planning decisions. However, there's a dearth of computational tools that focus on the industrial sector, including the steel industry. And in order to move from these very high-level agenda setting decisions to more detailed policy design and deployment decisions, we really need to evolve our computational tools to reflect both cost and non-cost objectives like equity, air quality, and labor. We need to evolve these tools to better incorporate supply chain dynamics and also integrate higher spatial resolutions. So the objective of this overarching research project is to facilitate public policy and infrastructure planning decision-making associated with US steel decarbonization while integrating cost and equity related objectives. So this diagram conceptualizes our convergent research design. So this research design includes computational modeling, expert elicitation, and the development of tools for decision-making. So with respect to computational modeling, we're currently developing a highly granular techno-economic and life cycle assessment of facility and industry level pathways. In addition, we're developing a multi-attribute decision model that not only includes costs, but other non-cost attributes as well that may be relevant for different types of decision makers and stakeholders. With respect to stakeholder elicitation, this entails technical expert elicitations of costs and policies, as well as interviews with stakeholders and communities that currently host steel facilities. Importantly, the computational modeling and the stakeholder elicitation tasks inform each other, and so they're not being done in isolation. And finally, at the end of the project, the intention is to develop an online mapping and scenario platform for use by multiple stakeholders. I also wanted to emphasize that we're very deliberate in the research design and how we're engaging stakeholders. So this is just a conceptualization of how our project tasks map onto a continuum of increasing level of community involvement. And so notably, this project design spans outreach, consultation, and involvement, but does not include kind of shared leadership with communities, nor is it community driven. To implement this convergent research design, we assembled an interdisciplinary team, including 2 engineering PhD students, Robin Zhao and Mike May, as well as Dr. Greenleaf, who is an anthropologist and a lawyer, Dr. Middleton, and myself, and so I'm a hybrid engineer and public policy researcher. So our research focuses on different crude steel production routes, including modeling materials, cost, and emissions over the life cycle or supply chain. And so this includes raw material production and preparation, upstream fuel production and transport, electricity generation, and iron and steel making. So specifically, we are focused on decision-making directly in the iron and steel making industry, which is outlined in purple in this diagram, but we're also modeling the interacting upstream dynamics and effects as well. The next 4 slides provide an overview of 4 studies that we're currently kind of working on. The first study focuses on the development of a techno-economic and life cycle assessment of crude production pathways, both at the facility level and industry level. So we're modeling facility level material, electricity, and fuel demand, emissions, and costs associated with alternative mitigation options. And we're also simulating the supply chain, so upstream emissions and costs, as well as scrap steel supply and future demand for crude steel. And as part of this study, later on, we plan to model alternative demand and supply side policies that will interact with the supply chain and facility level simulations. In doing the techno-economic assessment, we are increasingly understanding how uncertain a lot of the parameters like capital costs and prices are. And we also wanted to be able to better ground our modeling in expert understanding of costs, market shares, and technologies, as well as the suite of potential public policies. So we've done some informal expert consultation so far, but now we're starting to formalize a protocol to do an expert elicitation to elicit knowledge of cost, technologies, and policies. So far, the studies that I presented have been focusing on technology, cost, and emissions related considerations, but the scope of this project is more expansive than that. We expressly want to include other important distributional equity aspects. So specifically, we're planning to do a robust multi-attribute analysis of facility level and industrial-wide decisions, including attributes related to cost, climate, employment, and air quality, and to the extent that we can include other attributes. And so we're building on employment and air quality modeling tools and frameworks that we developed and used in the past for other sectors. And finally, we're also planning to conduct multi-stakeholder and mental modeling in communities that currently host steel manufacturing facilities. The objective of this task is to understand perspectives and values related to impacts and drivers of steel site operations and siting decisions, as well as the equity implications. So stakeholder interviews can provide information on how to more meaningfully engage communities in decision-making processes, and also the types of considerations that are relevant to include in our computational planning models. So in the last 4 slides, I showed different studies under the umbrella of this project. However, these aren't being done fully in sequence. Rather, we're trying to make the different elements interact to the extent that's feasible and useful. And with that, I'll end there. Thank you.
Great, thank you so much, Dr. Mayfield. So we are now going to hear from Dr. Rebecca Tez. She is an assistant professor of mechanical engineering and environmental and ecological engineering at Purdue University. Her research focuses on sustainability at the intersection of energy technologies, economics, and decision-making processes to minimize the cost of transitioning to new decarbonized energy systems. She's worked on new energy storage systems, transportation alternatives, and industrial decarbonization. I'll hand things off to Dr. Tez.
Great. So today I'm going to talk a bit about some of our ongoing work related to the impacts of renewable energy on manufacturing. And so just approaching industrial decarbonization overall, whether it's for this project or just in general, it's challenging because a lot of these industries have almost explicitly removed themselves from our broader electricity system, right? So they're consuming a lot of fuels, whether that's natural gas, petroleum, coal still plays a factor, and it's driving a lot of these overall emissions. And then there are also just unique process level challenges where there are emissions that are coming from chemical reactions unique to specific industries. And so if we think about this sort of holistically, identifying what those processes and those chemical reactions are is part of the challenge for thinking about decarbonizing this industry overall. Steel, cement, petrochemicals are some of the sort of largest contributors to industrial emissions in the United States. And collectively, those three industries employ about the same number of workers as energy extraction industries. So we've talked a lot about, and there's research related to having a just transition for workers who are in sort of energy extraction or oil and gas or other industries that might change with a decarbonization transition. But there are potentially more employees, if you think about industry overall, as part of a decarbonization transition. And so the steel industry presents an interesting case study for this transition because they already have an electrified footprint. And so as Dr. Mayfield mentioned, and had some slides, that our recycled steel industry in the United States is already largely electrified. So we're using these electric arc furnaces. And then there are technology pathways for decarbonizing other steps in these production processes. We focus a lot on sort of using hydrogen as an alternative to do the reduction of iron ore into pure iron that you could then use in these electrified pathways. And so the questions that we were really interested in answering are, what are the attributes of sort of people who are currently in the steel industry and their jobs? What attributes are most important to them? So we know things like wages are important, things like benefits, healthcare are often important. But what about other considerations like the hours that they're working, the flexibility, the predictability that they have, and how do those things contribute to sort of their quality of life and their ability to balance both their work and non-work responsibilities? And then thinking about, if we are in this future where we've got a low carbon electricity system largely based on renewable energy or with significant contributions from renewable energy, how do those patterns in renewable energy availability and cost influence our ability to produce both the hydrogen that could potentially serve as an input to the steel manufacturing, but also these steel plants themselves, when we're thinking about both energy, labor, and equipment costs, to come up with socio-technical solutions that will both balance sort of the needs of workers and what people are looking for as, you know, jobs. It's just a portion of their sort of overall life and goals, with our sort of need to be able to produce steel at prices that's competitive with other sources on the global market. And so to do that, we combined our research methods will draw from both social sciences and engineering. So on the social science side, we've done a lot of exploratory interviews with people who are currently working in the steel industry to get a sense of how they think about their jobs and things that are important to them. We're using that to inform the design of an online choice-based conjoint survey so that we can tease out how workers in this industry are trading off between different job attributes overall. On sort of the more engineering side, we're looking at hydrogen electrolyzers. And so these polymer electrolyte membrane electrolyzers are a technology that's existed for a long time, but they're often, they've to date been a bit expensive, but they offer the flexibility to use renewable energy and use variable sort of power inputs to produce hydrogen. And then having both of those inform this process-based modeling that we can use to estimate techno-economic costs, and also the emissions associated with steel production. And then sort of underpinning all of this is we have to have some sense of what might happen to this low carbon electricity grid. And so we're using an off-the-shelf open source model from out of NREL. So it's the NREL's READS model to just get a sense of some scenarios of what the broader electricity transition might look like as part of this low carbon transformation of the steel industry. And so we've conducted 15 interviews to date. It's been a roughly equal split between people who are unionized and non-unionized. And we've gotten a decent cross-section of the steel industry as it exists today. So people who are working in some of these facilities with electric arc furnaces, people who are working in facilities with blast furnaces. And so from that, we've noticed a few key trends. The first is that wages often include not just sort of a base hourly pay, but also some sort of incentive that's tied to the productivity of these facilities. Depending on whether they are or are not in a union, the percentage of pay that can be attributed to this incentive really varies a lot. So non-unionized roles typically have a very, very high sort of percentage of compensation as this incentive pay, whereas at unionized shops, it's a little bit smaller. We've noticed that rotating schedules are common, especially in higher skilled roles, which is a bit of a surprise. And so what that means is instead of somebody working a day shift all the time, what they'll do is typically they'll work for 4 days. And so you'll work 4 12-hour shifts in a row over the course of 4 days. You'll have 4 days off, so you won't have to report to work. And then the next 4 days you'll report to work, but for night shifts. So you'll work 12-hour night shifts for 4 days in a row and then have another 4 days off, and then the whole cycle repeats. And so when we ask questions like how often work interferes with personal life, that schedule can be pretty grueling. And so there's a pretty decent sort of incidence of having some events where that interferes with personal life. Most of the people we talk to sort of asking the flip of that question is how often does their personal life interfere with work? We were conducting these interviews in person. A lot of the people that we spoke to either had grown children or had no children. And so they didn't necessarily have too many interactions sort of when their personal life interferes with work, although there were definitely some notable outliers. And I think as we move forward and look to the survey that's fielded online, figuring out sort of who's maybe having more challenges with balancing their work and personal life might be important as we think about sort of these jobs as just one component of people's lives. And then the last sort of group of trends that we noticed were sort of related to energy and climate impacts. So the electrified sort of portion of the steel industry is already participating in demand response programs, right? So on the hottest days of July, they're usually not actually running sort of the electric arc furnaces, and they are sort of monitoring and get some sort of participation with wholesale market pricing. In facilities that are still tied to fossil fuel use, they didn't necessarily see as much influence depending on energy availability or energy costs. But what they did notice was that depending on the outdoor air temperatures, they might not have the ability to cool some of the water that's used in their facilities to a temperature that is sufficiently cool that it can be re-released into the bodies of water where it was initially drawn from. So basically what's happening is they're drawing water usually from Lake Michigan, and if it's too warm, they cannot cool it sufficiently that they can re-release that water. And so they have these retention ponds, and as those ponds fill up, they have had to stop production because the temperature was too high and they couldn't release the water without having serious negative environmental consequences. And so there are some climate impacts that people have seen in recent years. Sort of the other piece of ongoing work has been related to these hydrogen production models. And so we were looking at things that might be influenced by local weather and local climate changes over time. And so we've started looking at things like temperature and relative humidity. And so usually there's sort of a sweet spot for the operating temperature of these electrolyzers. But as you sort of increase the temperature beyond that sort of minimum necessary, the higher temperatures will change the partial pressure within these electrolyzers, and it basically just means you're producing less hydrogen per unit area of reaction space, and so that drives up the cost of producing hydrogen. Similarly, there are trends related to the relative humidity, so it becomes more conductive as the atmosphere that these systems are operating in is more humid. And so from that, we can sort of combine them to come up with a specific energy consumption for producing hydrogen. And so you want to have these lower temperatures and higher humidities to have this reduced energy consumption. And so what that means is that when you then apply this to different locations in the United States, there are different trends in the total energy consumed to produce a kilogram of hydrogen associated with different regions of the United States. So Florida, where it's hot and humid in this sort of time period, was showing a lower energy consumption than parts of sort of Pacific Northwest that tend to be drier. And at this point in time, I think you needed to add more energy to meet sort of this minimum threshold operating temperature. We're also looking into things like the pH of the water that's available, right? So these might not be insignificant quantities of water to support these industries. And the characteristics, especially the pH of that water, might also play a role in the energy consumed, but also the sort of useful lifetime of some of this hydrogen production equipment. And so again, we are also sort of in the first year of this project. And so the next sort of steps are to field this larger survey to get perspectives from more workers in this industry, to continue considering how the environmental factors influence the cost of producing hydrogen overall, so including sort of the lifetime effects on some of the capital equipment associated with it. And then as we sort of move forward, thinking about how the electricity consumption associated with some of these industries might change demand for electricity in different regions. So we've got some preliminary scenarios, but I think adding the increased electricity consumption might add significant electricity load to different geographic areas. And then also just considering the equipment costs alongside energy and labor costs to identify some of these socio-technical pathways for steel production. And so with that, I'll acknowledge the students and some of my collaborators, Professor Partha Mukherjee and Jeremy Reynolds here at Purdue, and the students who've helped support this project. And then again, acknowledging that this has been supported financially through a grant from the Alfred P. Sloan Foundation. And I will leave it there.
Great, thank you, Dr. Tez. We are next going to hear from Simon Masala, who is the Managing Director at DC Muse, an organization that convenes a diverse team of researchers and industry experts dedicated to decarbonizing the chemical industry via electrification. He's experienced in operations management, supply chain management, project management, stakeholder management, audited financial statements analysis, and various other areas. And Mr. Masala leads DC Muse toward its vision to catalyze the decarbonization of the chemical industry by innovating chemical manufacturing processes powered by sustainable electricity grids.
It looks like I'm unable to start my video.
Yeah, 1 second, we'll try to adjust that.
Okay, thank you. Let me share my screen. Good afternoon, ladies and gentlemen. I'm Simon Mashala, privileged to serve as the Managing Director of DC Muse. We are a New York University-led center dedicated to advancing the cause of decarbonizing chemical manufacturing using sustainable electrification. Today, I'm honored to shed light on our organization endeavors in the realm of climate change. Let's delve into the intriguing origin of DC Muse. The story begins with a concerning reality, the dramatic surge in atmospheric carbon dioxide levels, largely driven by human emissions. In order to visualize this crucial narrative, take a look at the graph before you. The blue line represents the alarming rise of CO2 in the atmosphere, while the gray line illustrates the staggering growth of human emissions. This graph paints a vivid picture of our journey. Emissions, once at a modest 5 gigatons per year in the mid-20th century, spiraled upward, ultimately exceeding a staggering 35 billion tons per year as the 20th century drew to a close. Human emissions of carbon dioxide and other greenhouse gases are a primary driver of climate change and present one of the world's most pressing challenges. To set the scene, let's look at how the planet has warmed. In the chart, we see the global average temperature rise is in the range of 1 to 1.2 degrees Celsius. Our biggest impact is on the chemical industry. More than 93% of chemical processes use fossil fuel heat, there is about 96% of goods touched by the chemical industry, and it contributes 25% of US gross domestic product. How do we support economic prosperity without fueling climate change? So what did we do about this? We grabbed some friends and colleagues from other institutions. We put them across different functions. We have established a robust network comprising 13 universities and 2 national laboratories, which extends our reach across the entire United States. Together, we convene to explore the opportunities within our grasp. To provide you with a glimpse of our organization, we'll begin with a brief video presentation.
Earth's climate is warming, posing a severe threat to life on our planet. It is vital that CO2 being released into our atmosphere from all human activity is reduced to zero. Emissions from sources like transportation and power generation plants are being studied in detail, and economically viable greener alternatives are being deployed everywhere. Electric cars are beginning to replace gasoline and diesel-fueled cars, which draw power from the electric grid. At the same time, power generation for the grid is also becoming greener. Wind, solar, and other forms of renewable energy are becoming the new norm. However, the chemical manufacturing industry is lagging and must catch up. It does not yet have a coordinated decarbonization strategy. Despite this, chemical manufacturing produces materials which are found in over 95% of the goods we use. These include a diverse range of items that many of us use every day, from smartphones to shoes. The petrochemical industry breaks down crude oil, a fossil fuel consisting of a soup of hydrocarbon molecules, before reassembling them into useful compounds. Currently, over 90% of reaction and separation processes are unsustainable, using heat from burning fossil fuels. These emit over 3 billion metric tons of CO2 every year, heavily contributing to climate change. Our vision is to decarbonize these processes by replacing the unsustainable use of fossil fuels with electricity supplied from renewable sources, electrifying chemical manufacturing. By replacing heat-powered processes with those powered by electricity, sustainable energy sources, such as solar and wind, can be used, which do not emit any CO2. A greener strategy would be to simultaneously replace the crude oil feedstock. For example, using biomass, air, and water to create the reactants, resulting in a potentially carbon-negative process. We are DC Muse, the Center for Decarbonizing Chemical Manufacturing Using Sustainable Electrification. We are a multi-institutional effort made up of a diverse team of academics, companies, engineers, chemists, materials and data scientists, entrepreneurs, and many more. Our goal is to provide the scientific and engineering foundations for electrically driven means of chemical production. We aim to electrify the chemical industry and catalyze the transition to a decarbonized future. This means that materials produced by the chemical industry can be made using carbon-neutral processes, leading us towards a future in which we can be confident that the products we use every day are sustainable. We are going to change the chemical industry for good, for a greener future. Will you join us?
Okay, as depicted in the video, our mission involves a profound transformation of the chemical industry. In our current conventional setup, visualized in the first diagram, we rely on thermal energy from fossil fuels, directed reactants into chemical reactors, and then channeling the products and byproducts into a distillation column for separation, ultimately yielding pure products. However, our vision for change, represented in the second diagram, embraces a paradigm shift. We harness renewable energy sources such as solar and wind to power an electrochemical and plasma catalytic reactor. This innovative approach routes products and byproducts to a membrane separation unit, ensuring the production of pure, sustainable products. In our journey towards establishing DCMUs, we have structured our progress into 4 distinct phases. The pre-seed stage. This initial phase was made possible by funding from NSF, which enabled us to kickstart our journey and focus on center planning. Currently, we find ourselves in the critical phase of center formation in the seed stage. We are grateful for the support of the Sloan Foundation, which has provided us with 2 grants, propelling us forward in this pivotal stage. Our next milestone is the anticipated growth stage, slated for 2024 to 2026. During this phase, we aim to establish an industry consortium and forge strategic partnerships to further our mission. Our ultimate goal is to become government-supported center. Entering the impact stage, we are actively exploring avenues like STC, ERC, and more to secure additional support and extend our influence. DCMU's team is organized into 3 primary thrusts, each helmed by expert leaders. Electrochemical Manufacturing Trust, we have Dan Exposito, a pioneer in the field. For the System Integration Trust, is spearheaded by Derek, soon to join NYU from MIT, and Kyrie from University of Colorado, bringing a wealth of experience and knowledge. Plasma Manufacturing Trust, we have Ryan, who brings a strong vision and expertise to the team. Next, I will provide a brief overview of our ongoing research projects. Currently, Dr. Dan Exposito is focused on engineering electrocatalytic materials and devices to support the sustainable production of fuels and chemicals. Derek is leading the Sustainable Energy Transitions Group with a focus on process and enterprise level analysis. The primary objective is to advance technology, R&D, and assess the impact on energy systems. Ryan is actively involved in research related to unconventional reactors for plasma heterogeneous catalysis. So our team has an extensive list of publications showcasing our research efforts. As an example, Kyrie and her team have published a noteworthy study titled Techno-Economic Analysis of Electrified Ethylene Plant Operation under Receding Horizon Control. We are solidifying our position as leaders in the field through our contributions to the prestigious journal Joule, which now boasts an impressive impact factor of 46. Thank you.
Great, thank you. So our last presenter is Dr. Avi Stolz from the U.S. Department of Energy's Industrial Efficiency and Decarbonization Office. Dr. Stolz leads the office's strategy to accelerate the innovation and adoption of cost-effective technologies that eliminate industrial greenhouse gas emissions. Prior to his time at DOE, he was the program manager for concentrating solar thermal power for another DOE office, the Solar Energy Technologies Office. And before coming to the Energy Department, Dr. Stolz was a postdoctoral fellow at the University of Amsterdam after getting his bachelor's and doctoral degrees in chemistry from Columbia and Northwestern, respectively. Dr. Stolz.
Apologies for that. Just took me a second to find the unmute button. Thank you for the introduction, for the kind introduction, and for the invitation to have me here today. So I'm going to maybe take the conversation up a couple of levels from the previous presenters who gave some really interesting presentations on specific opportunities for industrial decarbonization. I'm going to talk a little bit about the entire landscape of industrial decarbonization that we're really focused on here in DOE to get the entire sector towards our goal of a net zero emissions economy. If I can advance my slides, let's see. There we go. So again, relatively high level point that I think the other speakers have made as well, which of course is that when we look at the industrial sector, it is a critical end use overall that we need to work on to get to overall decarbonization. It's about a third of the US's primary energy use, as well as about 30% of energy-related CO2 emissions, even a little bit more when you take into account process emissions like from cement manufacturing that inherently produce CO2 through chemical through chemical processes inherent to the technology. And this is, of course, a growing problem. We anticipate industrial sector energy demand increasing if we do nothing by 2050. So it's not just today's industrial base that we need to decarbonize, but future technologies as well. And we need to do this without damaging the critical role that U.S. manufacturing industry plays in the U.S. So when we talk about decreasing CO2 emissions and industrial decarbonization, I want to be perfectly clear that our strategy at DOE for industrial decarbonization is not industry, it is deindustrialization of the U.S. Rather, we need to work on developing these technologies in a way that makes the decarbonized technologies at least, if not more, cost effective than today's incumbent fossil fuel-based technologies. This is, of course, a really challenging problem. So if we think about some of the systemic barriers to industrial decarbonization, first is, of course, the scale of the cost we're talking about. So we in DOE recently released a report that we call our pathways, in a series that we call our pathways to commercial liftoff. And we just released a couple of reports in this series specifically focused on industrial decarbonization. And it lays out that just for the US, just for 8 industrial sectors that specifically were focused on in the Inflation Reduction Act. So you see the 8 sectors there. We're talking about a cost on the order of $1 trillion required of capital investment to decarbonize these technologies. And it's not just a question of finding the money, it's a question of the technologies themselves and whether or not we have them. That same report estimated that using today's commercial technologies, only about 40% of emissions are addressable by are addressable with technologies that are cost effective to deploy today. That means, of course, that there are 60% of emissions that essentially require novel technologies, or at least not yet commercialized technologies, to be developed in order to reach our goal. What that means, of course, given the scale of the challenge, is that in DOE, our entire strategy is really thinking about where the targeted investments are with our, limited, relatively compared to the scale of the challenge, limited ability to provide funds, where we can really have targeted investments to address this challenge. Just another couple of quick words about really the systemic barriers to industrial decarbonization. And I think this is, something that will be familiar to much of the audience, but that we can't really be talking about a one-size-fits-all solution for industry. Of course, when we talk about industry as a sector, we're not talking about one sector, but really many, many, many industrial subsectors. This is just showing a list of the emissions associated with some of the top most highly emitting sectors in the U.S. Of course, one of the challenges with industry is that you could, this chart could take, could go down to the bottom of the slide even further with the number of different industries and sectors that we're addressing. And even if you look at, the highly emitting sectors here, so take, for example, chemicals, the top row in that chart, that's not really just one sector, but it's really many, many different products and processes that are involved in that. So the chemical sector is really, the manufacturing of basic organic chemicals, plastic materials, ethanol, basic inorganics, industrial gases, fertilizers, et cetera, all of which are really fundamentally different processes and products. You could also, of course, subdivide the industrial sector rather than by product or by subsector, instead looking at the unit processes that are involved. And of course, and again, there's not going to be a one-size-fits-all solution. There isn't any single energy use and energy process that if you solve the entire problem. There is, of course, one big one that's about half of the energy use in industry, which is process heating. But even that, it's a little bit misleading to think of as a single unit process. When you think about the distribution of process heat in the industrial sector, you're talking about everything from relatively low temperature heat at below 80 degrees C used in a lot of, for example, food processing, all the way up to very high temperatures above 1100 degrees C used in cement processing, cement manufacturing facilities, iron and steel facilities, and others, and everything in between. And again, there's no one technology, looking at that wide range of temperatures that is going to solve all of our problems. So of course, it's not just challenges that we have in industrial decarbonization. We do have some tailwinds supporting us as well, particularly, of course, with the recent legislation with the Inflation Reduction Act and bipartisan infrastructure law, which represents an investment of more than $430 billion in modernizing the American energy system. And a significant amount of that is relevant to and directly going towards industrial applications that are benefiting our programs. I'll also say that we have started to develop, of course, a strategy in addressing this in DOE. And about a year ago, we released our industrial decarbonization roadmap that really lays out the analytical foundation describing the technologies that we need to develop that we believe are going to be essential to achieving this net zero goal for the entire industrial sector. And we did that in the roadmap by looking at analytically by looking at the 5 highest emitting subsectors. So again, iron, steel, chemicals, food and beverage, petroleum refining, and cement, and looking at the technologies that can decarbonize those sectors along 4 primary technology pillars. And so that represents energy efficiency. So how do we decrease the total amount of energy that we need to apply to these systems? Industrial electrification. So how can we use a low carbon grid, a developing low carbon grid to replace, for example, fossil fuel combustion? Low carbon fuels, feedstocks, and energy sources. So how can we couple industrial processes directly to on-site use of low carbon energy resources? And then finally, carbon capture, utilization, and storage. And that's a recognition both of the role CCUS may potentially play in helping to remediate existing or ongoing use of fossil fuels, as well as, of course, those inherent process emissions like in cement manufacturing that produce CO2. So that roadmap, again, laid out kind of the analytical basis to show that we believe this is a technically feasible goal for DOE and for the US. And I won't get into the details here in the interest of time, but just to say that, again, we kind of laid out what the relative contributions of those different pillars and technologies are in this phased approach, and when we believe those technologies could potentially contribute to the overall goal of decarbonization. I'll make just a point here, and I know I'm starting to run out of time, that we're thinking about this and the technologies that we need at multiple different scales of technology deployment and system development. And when we think about those technologies that we need, there are technologies that we're going to need at the core process level. So we need to think about redesigning inherent processing technologies. We need to think about the redesign of industrial facilities. So how do we integrate low carbon technologies and, say, electrification technologies for low carbon fuels at the campus level, at the facility level that are currently designed for fossil fuel or high carbon or high emission technologies? And then how do we think about integrating beyond the plant bound? So if we're thinking about hydrogen, for example, as a key low carbon fuel, what does the future hydrogen network potentially look like that we're integrating with? What are going to be the challenges, the cost signals that we need to work with when we're redesigning these industrial systems? Or, for example, electrification. As we all think about electrification of these technologies, assuming that we have a low carbon grid, it's likely that the price signals of a low carbon grid and the integration challenges are going to be very different from today's grid. So how do we think about redesigning industrial processes to most effectively take advantage of the strengths and weaknesses of a low carbon grid? Just a couple more things I'll go through, hopefully quickly. We are working in DOE in a full ecosystem of technology development. And I'm really happy to say that, and it's really enabled by the investments we have from IRA and Bill, where we're able to take in DOE ideas from the very beginning of foundational science. And we have offices and teams that are able to go from that foundational science all the way up through applied R&D, piloting and validation, large-scale demonstration, deployment, and adoption acceleration. And where my office fits in, so I direct the Office of, the Industrial Efficiency and Decarbonization Office, or IEDO, and we really sit where, and I think in that sweet spot of identifying the technologies that we believe are promising, that can play a key role, seeing those developments coming from early stage science and engineering, and shepherding those technologies up through the initial technical de-risking and piloting and validation so that the fundamental technical risk of these technologies is retired. And therefore, what we have in our office is really the technical expertise of developing those industrial decarbonization systems. We can then work with our colleagues in other offices that have the functional expertise in large-scale project management, financing, market development, and work with those offices to fully commercially de-risk the technologies that we believe are going to be really critical. I'll also just very quickly mention that on that research, development, and demonstration side, of course, we're not the only office doing work relevant to industrial decarbonization. We work closely with other offices in DOE that are focused on, say, the low carbon energy sources, so solar, hydrogen, nuclear energy, as well as the carbon capture side. We work closely with our colleagues in the Office of Fossil Energy and Carbon Management. And we have various structures in DOE to ensure that we're working collaboratively and productively together. Maybe I will just do one more slide because I know I'm running short on time. Just to say a word about how we're organized within our office. And fortunately, while we're a relatively new office, so we're just a little bit more than a year old, we were stood up last October. We organize our work along three primary pillars. The first is our energy and emissions intensive industry subprogram led by Paul Meistrick. That's focused on and actually, maybe let me just jump to the next slide. That's focused on the system level and subsector specific approaches that are going to be required for these most highly emitting industries. Our second R&D subprogram is our cross-sector technologies subprogram led by Isaac Chan that's focused on, of course, the cross-cutting approaches that are going to be required, not just for those highly emitting sectors, but the entire industrial sector overall. So thermal processes and systems is a big portion of this, of course, focused on electrification of process heat, novel highly efficient thermal engineering systems, utilization of low carbon fuels, feedstocks, and energy sources. So thinking about, for example, things like how do we effectively utilize hydrogen combustion and generate low carbon heat. Emerging efficiency, so industrial load flexibility, potentially thermal energy storage to couple with intermittent energy sources. And then we also have a water and wastewater treatment portfolio as part of that team. And again, I'll skip through a couple things in the interest of time. The last thing I'll just quickly mention is that our final subprogram is our Technical Assistance and Workforce Development Program, and they work directly with existing industrial facilities and companies to develop the resources, tools, analysis, partnerships, networks that companies need in order to, today, make the decisions that they're able to start down their path of energy efficiency and decarbonization. And the absolute final thing I'll say is just to say that we just recently announced a new fellowship program for folks who are potentially interested in working with us, so specifically geared towards folks, early career scientists and engineers. If you're interested, if anything I said today interests you, please take a look at our fellowship program, and we'll be reviewing applications on January 15th. So please apply before then. And I'll just leave my final thank you slide up here with an invitation to subscribe to our newsletter to get more information on our work as we announce it. And just want to thank you all for your attention and happy to take questions. Thanks.
Great, thank you, Dr. Stolk. So I'll invite all of our panelists to turn on their video and we will have a discussion. Anyone who has questions in the audience, feel free to use the Q&A button at the bottom of your Zoom screen and you can submit those. We'll take as many as we have. We have a few that have been submitted and some others that we've come up with here, so we'll get things started. So I guess as an opening question that I think is relevant to all four of you, all of you are engaged in projects that use multiple methods from multiple disciplines. So can you talk a bit about some of the challenges and advantages of interdisciplinary research, and from there, sort of what advice you might give to other interdisciplinary researchers? Anyone interested in starting off?
I'm happy to start. Certainly from our perspective, as an applied R&D funding agency, I mean, I think we believe it's critical that all of this work is interdisciplinary. So when we're working on a technology that is going to actually be deployed in the real world, we need to be just as interdisciplinary as the companies that are deploying these, which is to say that we need chemists to understand kind of the fundamental reactions. We need chemical engineers to understand how this integrates into a fully flowing system. We need mechanical engineers to design the mechanical components. All is to say is this: none of this works unless the entire system works, and that's inherent to the way we approach programs and what we frankly strongly encourage in our solicitations to receive applications that are fully interdisciplinary and fully geared towards those real world systems.
Thank you.
So maybe I'll jump in for a second. So I would say I actually don't know how to do disciplinary research. I'm a trained interdisciplinary researcher like Dr. Ches in engineering and public policy. And if you focus on kind of solving a problem and working backwards from there, you realize that you necessarily need interdisciplinary tools and to collaborate with different people. I would say kind of there's challenges in that because you're often talking in different terminology. And so there's kind of the need to step back kind of and listen and trying to translate between disciplines. Also, with respect to kind of our research scope for this project, there's a lot of like interacting elements. So for example, if we're trying to elicit values to inform our modeling, but then we're trying to kind of model a system and there's constraints on what we can actually model in terms of values and other considerations. So that kind of presents challenges in interdisciplinary research in the scope of our project.
Yeah, I think I would piggyback on what Dr. Mayfield said. Definitely, you spend a lot of time translating between different disciplines. And then there just are questions that, engineering specifically might not be well suited to answer. And so you have to sort of draw on other, especially social science methods where you're actually able to engage with stakeholders and with people who are more involved in these systems. And so engineering sometimes will touch on some of these product design and product development methods, but drawing on like the strong social science components of how these systems might interact with communities. And I think, if the ultimate goal is to figure out how we might transform communities, we should be thinking about the people who would be involved and be experiencing that from the beginning.
Okay, I would also like to add from what the team has already said. Here at DCMUS, we have different engineering disciplines like civil engineering, chemical engineering, electrical engineering. Someone might think that we are focused only on the chemical industry, but from the research side up until implementation of this project, you need interdisciplinary engineering teams, and there should be an alignment between all the teams. So we work together with all the engineering teams, including the chemist and, you know, all the different functions.
Thank you. So I think this one is probably most relevant for Dr. Mayfield and Dr. Ches. Both of your projects involve some element of a stakeholder engagement process. And can you, I'm wondering, each of you sort of touched on this a bit in your presentation, but can you talk a bit more about the decisions that you are making on which particular stakeholders to target and how to engage with them, and some of the difficulties that you've encountered in that process and strategies to engage in effective ways?
Sure. So we really leverage the fact, so I'm at Purdue, I'm in Indiana, and so we've really been able to sort of leverage proximity to really help with some of the stakeholder engagement. We've been talking to some of the local union chapters up closer to Lake Michigan, where some of these facilities are located. And once you sort of have the union buy-in, it's a lot easier to sort of get regular people who are working in these jobs to sort of engage with you. And then recruiting people from some of these other generally more rural areas where a lot of these electrified facilities already exist. It's generally sort of in our backyard. And so we've been able to sort of leverage that proximity to recruit people through those avenues. We haven't necessarily been working through companies directly. And so I think there's usually a little bit of hesitation for people to sort of be recruited through an employer. And so we've been able to sort of just through public communications engage with people who are working in these industries. They play such a large role in some of these rural communities that if you are targeting sort of steel workers in Montgomery County, which is where we were working with, there's not that many people. And so it's relatively easy to reach the people in the demographics that you're interested in recruiting through that way.
Thank you.
Yeah. So we have kind of two elements of stakeholder engaged research. One is technical consultations and technical expert elicitation. And that has actually been kind of straightforward. We have found kind of industry is kind of very willing to have kind of those technical conversations because there's kind of a need on their side as well to have a better understanding of different pathways. It's been a lot more challenging on the community side. So we're not kind of targeting directly kind of laborers like in Dr. Ches's work. We're trying to get kind of a smattering of different stakeholders, including residents that may live nearby, state and federal policymakers as well. And so kind of that we've kind of designated the first year of this project just to try to start to build out. We have some of those relationships, but start to build out more community relationships, and we have on the ground community partners as well.
Great, thank you. So I want to ask, I guess, maybe a couple for Dr. Schultz. So first, you discussed in the presentation, the scale of this challenge is huge, and solutions need to be customized for dozens of different industries and processes. As you discussed, your office developed a roadmap and these decarbonization pillars, but can you talk a bit more about how you are choosing projects and how you're choosing to allocate resources kind of on the ground?
Yeah, absolutely. And I know, apologies for the interest of time, I wasn't able to share all of my slides, but within what I want to emphasize is that what the roadmap was not just kind of a subjective sense of what binning technologies here and there, but by basing that roadmap on a quantitative analytical foundation, what we have is the ability to essentially model the quantitative contributions of each of these technologies and each of the potential pathways towards the mitigation of specific amounts of industrial emissions. So what that means is what we've been doing in our office is actually prioritizing the efforts in each of these areas, in each of these sectors, and in industry overall, and really understanding where we can get the biggest emissions return for our technology investment. And so what we've been doing in our solicitations is laying out those specific technology pathways that we believe are really going to be critical to achieve this industrial decarbonization. What our goal is as an office is to create a full portfolio that accurately represents that prioritization. So, what you'll see is if you look at our solicitations, is sometimes a shift from year to year on specific opportunities that we're asking for, and that's really based on extensive stakeholder discussion, extensive analysis, quantitative analysis that I've been talking about, review of course, the proposals we are receiving, learning from our existing portfolio of projects, and understanding where the gaps are in the existing research landscape and where we believe there are opportunities where we're underinvested in to potentially push things forward. So again, hopefully that clarifies it a little bit. We're certainly working on making as much of that information and analysis as public as we can. We're still in the middle of some of our internal strategic road mapping to be able to publicize all of that. So as I mentioned, we're still a relatively young office, so we're hopeful to share as much of that analysis soon as we'll be able to.
Great. And then there was also an audience question for you to talk a bit more about the partnerships you mentioned in the slides, and sort of, who are you partnering with? How can these partnerships help things kind of proceed faster? Sure.
Yeah. So there are different kinds of partnerships that we encourage. So certainly in our research development demonstration programs, we strongly encourage all of our projects to have industrial partners, or in fact many of our projects are led by companies, but even our projects that are led by universities or national laboratories, we strongly encourage industrial partnerships so that again to kind of bring that path to commercialization and market reality to our R&D. We also have in our RD&D portfolio what we call our Manufacturing USA Institutes. So these are large multi-organizational institutes. So for example, our most recent one that we announced is led out of Arizona State University, called EPIC-C, focused on process heat electrification. And what that is, so that's a 5-year, $70 million DOE with significant cost share brought by the various partners. So that's a multi-organizational institute led by a number of universities, national laboratories, and companies to create the full innovation ecosystem to take process heat electrification technologies from the lab, take them out of the lab, bring them with the test facilities that these partners bring to the institute, and actually then bring them to the companies that are members of the institute, and help them actually deploy it in a pre-competitive, a pre-commercial environment in which we can have those full open technology development discussions to really accelerate the technology advancement. In our technical assistance portfolio, we have a number of partnerships that are really geared towards information and analysis and resource dissemination. So, for example, one of our recent announcements over the summer was the launch of what we call our on-site energy technical assistance partnerships, or TAPs. And what this is a network of partnerships focused on on-site and industrial on-site energy technologies. So technologies like combined heat and power, solar photovoltaics, even on-site wind, geothermal, batteries, number of other technologies that are relevant to deployment on-site of large and small industrial facilities. And so what the TAPs are is a regional network of partnerships that we've set up. So 8 of these across 10 different regions of the US. And each of those partnerships is essentially a focal point in their region for bringing together expertise in, again, regional specific policy regulations, equipment analysis of equipment deployment, bringing together kind of the technical resources of that region, and offering that up to industrial facilities in the region that are interested in deploying these on-site energy technologies. And then we have a number of other, so that's just a little bit of a flavor of some of the partnerships. There are a number of other programs I could go more into detail of, but maybe I'll pause there in the interest of time.
Great, thank you. On a similar line, Mr. Masala, can you talk a bit about how some of the collaborative design of DCMUs has come together in terms of the researchers and university partners and kind of companies that are involved. How were different entities selected, and how did that all come together?
Yeah, certainly. So when we started DCMUs, like I mentioned in my presentation, this is NYU-led organization, but we work with different universities. So we looked at researchers that are working on decarbonization projects, all over the United States. We looked at their expertise, and some of these people were recommended to us as well, and we engaged with them, and we basically elaborated what our objectives are and what we wanted to achieve in terms of creating the DCMUs as well. And in terms of the industry partner, we look at their pain points, because the aim of DCMUs is to make sure that we solve the issues in the chemical industry. So we look at their pain points and we see how we can do research, here at the universities, and then be able to resolve our customers' issues. So that's how we basically collaborate. We look at those strategic partners, because we cannot engage, companies that won't be relevant to what we are doing, at the university. So that's how we basically selected the researchers, and as well as selecting companies that we work with.
Great, thank you. Dr. Mayfield, as you discussed, the final output of your project in part aims to inform decision-making. Can you talk a bit more about some of the decision makers and types of decisions that you think might benefit from this research, and how you're working to make sure that the output is decision useful?
So I didn't go over kind of that last part, the decision-making tool. And so we plan to kind of create an online platform that houses all of our data, all of our scenarios, and is kind of an interactive tool. We plan to do kind of in community or with different stakeholders testing of those platforms to make sure they're usable. Also kind of understandably, like not many of the people in communities, based on kind of initial information, do not kind of have access to these online platforms. So we're thinking about how to create other types of kind of communications to provide kind of support for community members. That's kind of on the back end, kind of the decision-making tool and platform. But throughout kind of our modeling process, we have kind of these two stakeholder engaged research elements. So as I mentioned before, kind of the expert elicitations, which help ground our modeling in terms of technical feasibility and cost, in addition to trying to identify the suite of policies that may be implemented. And so that's on the expert elicitation side. And on kind of the multi-stakeholder interview side, that is kind of more conceptual in terms of trying to elicit or understand people's values regarding the operations and decisions that are at kind of the community scale. And so that is kind of meant to inform the types of kind of objectives and attributes that we're modeling.
Thanks. So we had an audience question asking about what people who work in some of these industries might be able to do to help. Suggestions for people working who in industries who might want to support these kinds of research projects and efforts, but employers may or may not be willing to lend direct support. Do any of you have thoughts on ways that can be useful?
I think it sort of depends on what counts as direct support. Something that we've encountered in this project and some other ongoing work is that understanding like how energy use happens at individual facilities can be really, really different, even in the same industry. So having even just like basic data about like what temperatures people are using for process heat, what energy sources they're using, whether there's some capacity for energy switching or other sort of resources that already exist, and just having that data available somewhere could be hugely helpful as we think about some of these more time dependent energy sources playing a larger role, and really just understanding what different facilities within industries actually are using energy for and how they're using it.
Thank you. So I guess building off that somewhat, Dr. Ches, your research involves using and collecting data on so many different issues, labor issues, weather, electric system operations, industrial technology. Can you just talk about how you've approached project design, how you've identified data sources, addressed data gaps, what that has looked like so far?
Yeah, and so we sort of my expertise is not necessarily in electricity systems models, and so where we knew that there were existing resources that we could use that would be close enough approximations to give us at least a starting point for modeling what these systems might look like. So especially on the electricity side, taking from open source tools that already exist was a big part of being able to sort of scope this and really focusing on our efforts on things that we thought we would be bringing sort of unique expertise to. Some of the pieces on the hydrogen side have sort of just come out of the actual modeling exercises that we've done to date. And so we want to sort of more deeply explore some of the water quality issues, especially. And so it's not necessarily something we had originally set out to do, but it's something that we think is probably interesting and relevant moving forward. And so wanting to dive deeper into that. And so it's really just been a result of the project and where we've seen our modeling efforts take off. And then again, incorporating a diverse project team that has expertise in some of these social science methods that we're collecting data that's useful and can be translated between some of these engineering, techno-economic models and just good quantitative social science as well.
Thank you. So I know we're running short on time. I have one more question for Dr. Schultz and then one that I'd love to get everyone's thoughts on to close things out. So first, Dr. Schultz, can you talk a bit about how the office thinks about cross-sectoral challenges, things like grid capacity for hydrogen or the role of carbon capture, utilization, storage, these kinds of topics that are clearly very relevant to your work, but also sort of cross into many other areas?
Yeah, no, it's a good question, and frankly a really challenging question, right? Because it's of course the fundamental question of how do you aim towards a moving target, right? We're not there yet, right, in terms of, for example, a low carbon grid. So what does it mean for us to be focusing on electrification? Well, what we think it means is that we can highlight some specific research challenges that we believe are going to be essential. So for example, with grid integration, what we know about a low carbon grid is that, and frankly, even with today's grid, that cost of electricity is going to vary with time. Today's, and that's going to be even more important going forward. Today's industry, of course, is not set up very well to take advantage of that. So that's an example where we believe, for example, that there's a really promising opportunity to develop flexible industrial technologies. Now that may mean fundamental process redesign to enable industrial flexibility in a way that, for example, today's thermal processes that may go through fundamentally use large thermal mass heat exchangers or vessels or systems. Maybe with next generation electrification technologies, there are opportunities to a little bit more flexibly, or potentially, there are other technologies like, for example, thermal energy storage that allow you to use electricity on a variable basis, but remain continue to have a constant industrial process. So essentially decoupling the industrial processes from the energy sources. So those are the kinds of things we're looking at. Certainly carbon capture, utilization, storage is another a good example of kind of the challenge there. And so what we're really focused on is again the integration challenges of that technology, right? So we're not, I think as I mentioned, we're not developing the carbon capture technologies themselves. We're working closely and kind of allowing our colleagues in the Office of Fossil Energy and Carbon Management to take the lead there. But what we are focused on is, well, if that technology works, and if we assume that those technology targets are met in terms of cost and some of the engineering considerations, what are the opportunities that enables in industrial processes? So for example, a big focus in our chemicals portfolio is not just thinking about the energy inputs, but the feedstocks that are going to be required specifically for hydrocarbon based chemicals. And of course, we think that there's a really promising opportunity, assuming that we can get some of that carbon capture network to work, to utilize CO2 as a potential feedstock instead of petroleum-based resources. So that's something we're exploring, but of course we're doing that research in, while looking towards what those real, carbon networks in the future are going to look like, and what realistic pricing and, system constraints are going to look like. So all that's to say that it's a challenge. We're thinking about it and trying to be as prudent as possible and forward-looking at the system level as we develop those technologies.
Thank you. So we're about out of time, but I just want to end with a quick sort of lightning round question and ask each of you where you see kind of key research gaps in the area of industrial decarbonization. What are the research questions that you think need to be getting more focus in the policy or research and policy community? Anyone want to start us off?
Yeah, I think I need to add from what Dr. Schultz has said. We are working with one company actually that is using coal as a feedstock in the chemical process. And the challenge with coal is, it has got a lot of emissions, CO2 emissions, greenhouse gas emissions. So they are looking at alternative carbon source and hydrogen source. I think that should be, a critical focus in decarbonizing the chemical industry, So I think that's one major research project that, we need to be vocal about. We need to look at a lot of opportunities about that.
Sure, maybe I can jump in and share something. So I think from our perspective, one of the really big challenges, and I've talked a little bit about this, is grid integration. And really, I think from our perspective, this has been a hugely untapped resource and potential, not just potential challenge for industrial decarbonization, but potential opportunity for industrial flexibility and load service. So I think it was one of the previous presentations talked a little bit about kind of existing demand response in industrial facilities. I think that has certainly happened, but I think from our assessment, this is a hugely untapped resource, especially if you look, for example, at what's going on in, say, the residential and commercial building space and the level of sophistication with which utilities and analysts are able to analyze the opportunities for flexible load integration with low carbon grids. Where we are in industry, and for those of you doing research in industrial spaces, there is just a huge absence of available data to be able to do the detailed grid modeling that would be required to really validate the value of complex, sophisticated grid integration and grid flexibility. And so what I really want to call out is even before doing the work, the research on grid integration, just even getting the data and not treating industrial loads as just a black box that something happens behind the meter and the utilities have no idea what's going on, which is essentially the way it's treated in utility models today. Getting to that data availability, I think, could potentially open up a very, very fruitful area of research for industrial decarbonization.
And I would definitely sort of agree with the data availability, especially I think a lot about if there are smaller sort of industries or facilities that might have sort of an outsized role in sort of the overall emissions. And so how do we identify, I think we spend a lot of time talking about these like big industries and big facilities that are obviously a huge contributor, but are there also sort of smaller facilities that we could maybe make more bang for our buck initially to do decarbonization there? And how do we identify those, especially with these big data problems? They're not necessarily even large enough to show up on some of these large databases of current emissions. And so how do we identify where those facilities are? And again, their sort of unique energy needs that are associated with that.
Yeah, so I agree kind of on the data front. I also say I think needs to be additional research on kind of the value of and design of place-based research. And so even just doing some work kind of on the power sector side, seeing kind of the effects of place-based policies within the Inflation Reduction Act. There are kind of marginal effects that aren't actually going to potentially do what they want to do. And so how can we kind of take learnings from that to kind of better design place-based policies for the industrial sector? I think another thing that we don't have a good grasp on, if we're trying to make kind of facility level decisions, how does that kind of percolate into kind of upstream effects or supply chain effects? So oftentimes you have kind of very kind of integrated systems, such as if you kind of close or alter kind of one facility, kind of there's another facility that is directly kind of integrated to that, and that will have implications for those facilities. But we don't necessarily kind of know the supply chain and flows between these facilities.
Great, thank you all. Hopefully we will see more research in all of those areas soon. So I think we're out of time, but I wanted to thank the Sloan Foundation for supporting both this webinar series and so much great research in this space. I also wanted to thank my colleagues Kurt Weatherford and Virginia Nell for all their work organizing the event. And of course, thank you to our speakers and for everyone who joined. We look forward to seeing you all at one of our future webinars in the series. Thanks.